Well, hello guys, Mr. G here with another video from the question paper in June 2016 that was done in the Northern Cape and the Free State Province. This time we're going to be answering the last question of the paper, which is question 1. We answer all the other questions before, and then question 1 is the last one we have left. But before that, please subscribe for the channel so you can get all the notifications and videos and worksheet, etc. Now, 4 options are provided as possible answers to the following question. Each question has only one correct answer. All these ones are multiple choices, so you have to select the correct answer. The first one, question 1.1, says which one of the following represent a scalar quantity? Now remember, scalar quantity has only direction. So that is the characteristic of scalar quantities. Okay? Now, work is a scalar quantity. You must learn that work is a scalar quantity, and the minus here doesn't mean direction, it means something else. It means that energy is being taken from the system by that specific force. That is the negative work meaning. So question 1.1 is quite simple, it's A, nothing to worry about. Question 1.2, an object x mass m is moving at constant velocity along a smooth horizontal surface, so there's not friction, and it's moving at constant velocity. An identical object y is dropped into the object x and stayed there. Which one of the following represent the velocity of the system xy? Okay, so let's see what we have here. We have an object of mass m. Now object x has an initial velocity, okay, which is v, and it has a mass x. This is x. You have a mass x equal to m. Alright, now we have another object which is object y. It is identical, so my is equal to m as well, and the velocity, be careful with the velocity of the object y. Okay, so now we have in here a before in which the object is moving. Let me say, I want you to understand this one. The object is moving initially to the right, and another object with the same mass is being dropped. Another object which have the same mass is being dropped down on this one there. So it's been dropped. In actual fact, it's going to move down eventually. Okay, so this is what we have now. Even this one is before. Okay, so what is happening here, guys? This one is momentum. Initially, the object, the first one, the car, object or whatever it is moving to the right, and another object is being dropped, so it's moving down. So the momentum, which is a vector quantity, we have to select what direction are we going to work with, and we are going to work on the right direction. This one is the direction we are working with. Okay, so in this case, momentum is going to take the direction to the right. Therefore, for instance, if we say that the initial momentum of object x plus the initial momentum of object y is equal to final momentum of object x plus final momentum of object y. This one is the law of or principle of conservation of momentum. Momentum is mass multiplied by velocity. So mass x, which is m, multiplied by the initial velocity of x, which is v, plus mass of y multiplied by the initial velocity of y, but the initial velocity of y is dropped, and therefore the initial velocity of y in x is equal to 0. So all this one here is going to be equal to 0 because the initial velocity of y in the x direction is 0. Then in the final direction, or in the final or after, we have mass vx plus mass vy, but vx and vy is the same because they are moving together, right? So now how do we calculate this one here, or what we have at the end? We have mv equal to v, because they're moving together, bracket mx plus my, which is the same. So we are having mv equal to v multiplied by 2m. Alright, and when you substitute to calculate the v, which is the one, which of the following represent the velocity of the system xy, which is the final velocity, the v is equal to mv divided by 2m. When you work this one, you have that v is equal to v over 2. In other words, it's half v, which is b. B is the answer. This is a good question, this one. Okay, let's go to question 1.3. A rock is dropped from a tall building. Which one of the following combinations correctly describe the acceleration and velocities of the rock while it is falling? Remember, acceleration is going to stay constant regardless what is happening. Constant and down. Constant down. And the velocity is going to increase because the object is moving down, so it's going to increase. So this is what we have to look for there. Acceleration is constant, so the only option is the options are B and C, but we're looking for one that the velocity increases, so the answer is C. Very, very simple. Let's go to question 1.4. Question 1.4 says, three separated identical blocks are in contact with each other in a straight line. They are at rest and smooth horizontal surface. So there is not friction here, guys. There is not friction. Each of these blocks has a mass of m, and each of them is m. Another block with a scale with the same dimension but with a mass 2m moving with velocity v collides elastically. It means kinetic energy is conserved as well as momentum, and in the same straight line with the three stationary blocks. As you can see there, what is happening. Which one of the following diagrams represent the situation immediately after the collision? And then we have these different situations here, A, B, and C. You can see all the possible situations there. Okay, now guys, this is an elastic collision, which means that the total kinetic energy is conserved. In other words, what we have initially is not any of these cases. This is what we have initially there. We have that the total kinetic energy initial must be equal to the total kinetic energy final. Alright, so what we need to know, if the two masses here are coming from this side initially, to keep all this constant, when it bounces and stay at rest there, that means that two of these objects must move out with the same velocity as that one there. So the correct answer will be the second one. D is the correct answer here. So if we go here, I want you to note that the total kinetic energy initial here is half 2 mass multiplied by v squared. This is the initial kinetic energy of this system. And if we work here, guys, when you simplify the 2's, then you are going to have mv squared. This is what you're going to have at the beginning here for initial. This is the initial one. Now if you go there and you try everything, the total initial must be equal to the total final, because the collision is elastic. So if we try here, for instance, let's see what we have on this side there. Here we have half, mass is 1, is m, multiplied by 2v squared. You see? So when you solve this one, you have then that is half mass, now is 4v squared. And when you simplify this one, it's going to be 2mv squared. No good. This one must be equal to that one there. So you have to try each of them, but it's very, very simple. So here, if you do the same here, it's half mass v squared. Most definitely is not the same as the initial. You go to the second one. The second one, now you have half 2m, because you have two objects there, but 2v as well. 2v everything square. When you solve this one, you have half 2m bracket, you don't even have to have the bracket there, 4v square, and when you solve this one, guys, you get that is 4mv square. Not good. And now if you go to the d1, which is the last one, this one here, then you have that is half 2m v squared. 2 simplifies with the 2, you have mv squared. That is what you have at the end, but at the beginning was also mv squared. There it is, guys, mv squared. So the correct answer is D. Now question 1.5 say a girl is standing on the surface of the earth and drop a ball. After the first second of its motion, it has displacement delta y. A similar experiment is done on the surface of the moon. What would the magnitude of displacement during the first second be if the gravitational acceleration on the moon is 1/6 of that on the earth? Ignore the effect of friction. So on the earth, we know that the displacement is equal to initial velocity multiplied by the time plus half acceleration due to gravity multiplied by the time squared. Now, if we work with this one, we know because the object is being dropped, this here is 0. This one here is 0. Okay? Therefore, we have that displacement is equal to half acceleration due to gravity multiplied by the time squared, but the time is 1 because it's for 1 second. So the displacement will actually be half multiplied by acceleration due to gravity. Okay? I hope you understand. This is because the time is for 1 second. Now, on the moon, we're using the same formula. Displacement is equal to initial velocity multiplied by the time plus half acceleration due to gravity multiplied by the time squared. This one is on moon. Okay? This one was on Earth. So, same story. We substitute here. The displacement is equal to half acceleration, but the acceleration is 1/6 of g multiplied by the time, which is 1. Alright, so we have at the end here that this one is going to be 1/6 of a half g. Therefore, if you look here, the answer, this that you have here is that one there, which is the displacement on the Earth. So the displacement on the moon will be 1/6 of the displacement of the Earth. And the correct answer then is A. I hope that is clear. So let's go to question 1.6. Okay guys, now question 1.6. A car moving at a constant velocity with kinetic energy k and the Gaussian displacement delta x in time t. If the car's kinetic energy changes to 2k, it will undergo a displacement of magnitude, and they give you 4 options there, in the same time at the new constant velocity. So we have 2 situations here. We have a situation when the kinetic energy is k. Remember that kinetic energy is equal to half mass v squared. In other words, we can say that kinetic energy is directly proportional to v squared. Okay? But now in the new situation, they change the kinetic energy, and the kinetic energy is going to be double. Alright? So if we rearrange this one here, we can say that Ek is directly proportional to a V, or we can say that V is directly proportional to the square root of the kinetic energy. Okay? That is important here. But now the kinetic energy is going to be double the initial kinetic energy. So it's going to be directly proportional to the square root of 2k's. Okay? And now for a constant velocity, that is important to know. Now for a constant velocity, when velocity is constant, then the displacement is equal to the product of velocity multiplied by time. Alright, now they telling you that the kinetic energy is double. If the kinetic energy is double, then the velocity is the square root of 2. So this is displacement here. This one is displacement there. The displacement here is going to be the square root of v, because it is from there. Therefore, the correct answer is going to be then C. Is the square root of. I hope it is clear. This is not that bad. It's a grade 10. It's a grade 10 question, but it's a little bit confusing, guys. Okay. So let's go to question 1.7. This question said, in the circuit represented below, the internal resistance of the battery is negligible. Obvious. At this point of the year, you didn't do internal resistance and you have this circuit. Which one of the following combinations correctly represents the changes in the reading of the ammeter and the voltmeter when the copper wire is used to connect the two black dots there? So they say you are going to take a copper wire and you are going to connect these two dots here. So if you do that one, that means that this side of the circuit is going to get out. Alright, so now you have -1 resistance that was connected in series. Alright, therefore the total resistance of the circuit is going to be a less, because now you have -1 resistance connected in series. It's going to decrease. That is what happening to the total resistance of the circuit. If the total resistance of the circuit decreases, it means that the current must increase. And this voltmeter here, the voltage is equal to I multiplied by R. Now this R is this R there, okay, and that one did not change. What changed was the total resistance of the circuit, so this one is going to therefore increase as well. So the answer is going to be A, increase. Okay, now we're doing question 1.8. Two blocks P and Q manufactured from the same material. That means that the frictional force is going to be not the same, but the coefficient of friction is going to be the same. They're telling you there. Okay, and with masses of 2m and m respectively are placed on a hypotenuse of a triangle wooden block as shown below. The distance between the blocks is x. The heavier block P is above Q. When they are released simultaneously, they move down the inclined plane at increasing velocity. Now, how is the distance x affected while the two blocks move? And they asking you what happened to the distance x there. Now, I want you to do something here quickly, or I want us to do something quickly. The first thing we're going to do is the free body diagram for one block, because it's exactly the same. The only difference is that they have change in mass. Okay, so we are going to calculate the acceleration for the blocks quickly. For each of them, we're going to calculate the acceleration for each of them, but we are going to do only one free body diagram because it's the same idea here. Alright, so here is the free body diagram, and it's going to be the same for both objects. The difference is going to be the mass. So the free body diagram will be exactly the same, but for different objects. Okay, so now we're going to try to calculate the acceleration for one of the objects. So let's say for Q, let's start with Q. Okay, the acceleration we're using Newton's second law in x. In x-axis, we have that net force is equal to ma. Okay, what forces are acting there? We have the weight in the x-axis, we have the frictional force, and this is equal to ma. But now we have to remember, we don't have numbers here, we only have letters, so we have to get the weight in x. And if we go back here, according to this one, remember the angle is this one there, so it's going to be the opposite. So weight in x is equal to weight multiplied by sin of the theta, whatever the angle is not really important right now. This is equal to mass multiplied by acceleration due to gravity multiplied by sin theta. Okay, and we are going to substitute this one in there, guys. So what we have, mg multiplied by sin theta minus frictional force, but we don't have frictional force. Frictional force is equal to kinetic coefficient of friction multiplied by normal, and all that is equal to ma. So we're going to carry on. We don't have the normal. Remember, we don't have the normal, but normal is going to be equal to normal on this side here. Let's do it on this side here. Normal is equal to weight in the y-axis. You can see there. and then normal is equal to mass multiplied by acceleration due to gravity multiplied by cosine of theta, and then we are going to substitute there. So after everything we have mass, acceleration due to gravity, sin theta minus kinetic coefficient of friction multiplied by mass, acceleration due to gravity, cosine of theta equal to mass A. Alright, now we're working, remember, with either of the two objects. In this case, we're working for Q. Alright, so now here you can see that mg is a common factor. So we can say that mg, open bracket, sin theta minus coefficient of friction cos theta equal to ma. So if we calculate a now here, a is equal then to mg bracket sin theta minus kinetic coefficient of friction cos of theta, everything divided by m. And then, guys, we are near the end, because what we got here, the masses cancel each other. Remember, the idea is not to actually calculate the acceleration, is to see what is happening there. So if the acceleration is independent of the mass, in other words, the acceleration is going to be equal to the product of acceleration due to gravity, which is the same, it did not change, multiplied by sin of theta. Theta didn't change because it's the same angle. This one is theta here, minus kinetic coefficient of friction, which is the same, multiplied by cosine of theta. It means that the acceleration is the same for both objects, and therefore it will remain the same. That is the answer. I hope it's clear, this question 1.8. So we're going to see now 1.9. Okay, guys, let's see question 1.9. El ball is dropped from rest. Ignore the friction, friction. Which one of the following graph best represents the relationship between each of kinetic energy, gravitational potential energy, and mechanical energy as function of this placement? You need to know when the object is being dropped from certain height. As it drops here, the kinetic energy is going to increase from 0 because it's been dropped to a maximum kinetic energy when it's at the ground, all right? And the potential energy is the other way around. Potential energy started with a high value and is going to 0 when it's right on the ground because there is not height. The mechanical energy must stay constant. Mechanical energy must stay constant, and right in the center here must be the addition of the two of them, but the initial kinetic energy must be equal to the final kinetic energy, and that one, guys, is graph A. You can see that the potential energy, which represents U here, is go all the way down there. Potential energy is going all the way down. Kinetic energy is going all the way up, and you can see that the mechanical energy initial, which is the potential energy only, is going to be equal to the final kinetic energy or mechanical energy, which is the kinetic energy. So the answer is A. This question is quite simple. Then the very final question, which is 1.10. Finally, 3 electric point charges, each with magnitude of Q, are kept stationary in the same place at 3 corners X, Y, and Z of a right angle. The long and short sides of the right angle have lengths of 2r and r respectively, as you can see there in the picture, guys. The magnitude of the net electrostatic force on charge Z, we are talking about this charge here, is due to the two charges is equal to F. Now, I want you to note that this one here will form a triangle right angle, okay? So when you calculate the net electrostatic or the magnitude of the net electrostatic force at that point is going to be equal to square root of the electrostatic force due to X, I'm going to call due to X square, plus the electrostatic force due to Y squared. This one is Pythagoras, okay? That one is Pythagoras. I want you to notice that because we're going to use it just now. The charge at Y, the charge at this point here, move to a place at P which is half the distance before, all right? So the new force Y, or due to Y on Z, is equal to k qy qz divided by distance, but this distance now is going to be half the old distance, everything squared, because distance went half. Okay, so when you solve this one, guys, we did questions like this one before. To solve this is k qy qz divided by a fourth of r squared. When you solve this one, you get that the force is going to be equal to, or force due to y is going to be 4 times greater than before. Let's fix. I'm trying to fix this. Force y is equal to 4k qy qz divided by distance squared. The meaning here is that the force due to y increases at 4 times. So F net nu, working with nu, is equal to the square root of fx square plus f4 4 times the initial fy square. Now the question said, what should the magnitude of the new charge x be? What would the magnitude of the new charge x be so we can keep this constant or the same? Alright, so now guys, if the force y increases 4 times to keep this one constant, then the force at x must decrease 4 times. It's nothing to say, it's quite simple. So how can I change that one? By only changing the charge. Then the charge must be 4 times smaller. It's quite simple because the electrostatic force is directly proportional to the product of the charges. So to make the electrostatic force 4 times smaller, one of them must decrease 4 times. Therefore, x must be 1/4 of q. That is the correct answer. It's quite simple. It's a little bit confusing at the beginning, but it's not bad. So guys, thank you for watching. This is the end of the question, the end of the video, the end of this series of question paper 2016. It was a good question paper. I hope it helped. I hope you do well in the exams. I'll see you next time. Mr. G here.